you to our monthly webinar series and give you a little bit of background on eSig. For those of you not familiar with eSig, we are a membership-based nonprofit organization providing our members with objective information and resources for renewable energy and energy systems integration decisions. We also provide peer-to-peer networking opportunities, information and knowledge sharing, and professional education experiences. Our most recent activity was our annual Forecasting and Markets Workshop in Denver in June, and our next activity will be the Fall Technical Workshop next week in Charlotte. There's still time for last-minute registration, so please check it out if you haven't already. These workshops deal with a full range of issues associated with integrating wind and solar into electric, gas, and thermal systems. They also deal with the coupling to energy-consuming infrastructures, especially electric transportation, buildings, and industry. Information is available on the website on the upcoming workshop schedule for the next year, and everyone's invited to attend. eSig is a very unique organization, and I don't think you'll find anything quite like it anywhere else in the world. If you're new to eSig, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. You can find us at www.esig.energy, as well as on LinkedIn, Facebook, and Twitter. Okay, just a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid any unnecessary distractions. So please use the question and answer box in the lower right-hand side of your screen, not the chat box, to submit questions. That way we'll all be able to see them. And we'll try to save 10 minutes or so at the end for the Q&A. We plan to wrap it up at the top of the hour, and an email with a link will be provided once the presentation and audio file have been posted. We also plan to provide short responses to unanswered questions after the webinar, so don't be afraid to use the Q&A box. Okay, so today's webinar is on the topic of the use of probabilistic forecasts in theory and practice. It's a topic of very high interest to most everyone involved in renewable energy today, and has stirred up quite a lot of interest in the forecasting and application of batteries and battery hybrid wind and solar power plants recently. At the end of the webinar today, my hope is that everyone will be a little better informed and have a little better sense of the outlook for the use of probabilistic forecasts, which are becoming increasingly critical for the operation of power systems with a high share of variable renewable energy. The webinar will feature Ellen Haupt from NCAR, Tim Miller from SPP, and Pengwei from ERCOT. Sue received her Ph.D. in atmospheric sciences from the University of Michigan. She's a senior scientist and deputy director of the Research Applications Laboratory at NCAR, the National Center for Atmospheric Research in Boulder, Colorado, where she leads and oversees a broad range of weather forecasting applications projects. Sue's involved in a variety of industry activities and is a fellow of the American Meteorological Society. She's an internationally recognized author and speaker, and I consider myself lucky to count her as a colleague and a friend. Tim is manager of modeling and data integrity at SPP, the Southwest Power Pool, where he has 14 years of experience working in SPP's planning and operations organizations. During this time, he's worked on a wide variety of tasks, including the EMS real-time models and the day-ahead and real-time markets. Pengwei is currently lead engineer for renewable integration with ERCOT, the Electric Reliability Council of Texas. He received a Ph.D. in electrical engineering from RPI and has extensive experience in modeling and simulation and protection and control of power systems. I feel very fortunate to have Pengwei, Tim, and Sue here with us today. On a personal note, as I've gotten in the habit of doing, I took a look on LinkedIn yesterday, and I found out that Sue and I have over 70 shared connections. Tim, whom I've not known for quite so long, and I have 8 shared connections, and Pengwei, who must have spoken at eSig events at least a dozen times or more, I can hardly even find on LinkedIn. So I guess I need to spend more time at SPP and talk with Pengwei about LinkedIn. Sue and Pengwei, and now Tim, are active participants in eSig events, and I'm looking forward to what they have to say today. In this webinar, they'll discuss some of the leading ways that probabilistic forecasts are currently being used, show how they might be leveraged, additionally to enhance power system operation and planning. Sue will cover some of the background, and Tim and Pengwei will discuss how SPP and ERCOT mitigate risk posed by low probability and extreme conditions by using probabilistic forecasts. Okay, without any further ado, let's go ahead and get started. Sue, I'll now turn it over to you.
Okay, thank you, Charlie. I appreciate the great introduction, and I'm taking the meteorological point of view on how do we do probabilistic forecasts, why we do them. So I'm more on the theory part of this webinar, and then Tim and Pengwei will follow up more with the applications, the practice. So I want to say that one other thing that ESIG does, and at least Charlie does as ESIG director, is every couple years he configures a special issue of IEEE Power and Systems Engineering Journal. And he's recently done this, and one of the papers in that is going to be by a team of us on talking about this topic. So I want to acknowledge that although I led this paper, and Pengwei and Tim, of course, contributed major sections to it, we also have other co-authors who have contributed as well. And this paper will show up in the November-December issue of PES. So the seminar is loosely based on this paper and bringing in information from that. It won't cover everything, of course, because we don't have enough time to do that, but do please look at that paper and talk to the other co-authors as well. Now, first, I'd like to motivate why we're doing these probabilistic predictions. Okay, first of all, we want to be able to predict specific events, and I like using this one as an example that happened in Excel's Colorado territory some years ago. Each of the colors depicted here is power from a different wind farm in Colorado. And as you can see here, the day began with some passing thunderstorms, and then a cold front came through. And Excel saw an increase of 800 megawatts in their system of wind power, and then followed by an decrease of 800 megawatts in just a 4-hour period. So having situational awareness on an event like this is incredibly important to groups like Excel and other utilities and ISOs as well. But if we try to predict this cold front days in advance, we'll see that there's going to be one, but it's pretty hard to get the timing correct at that type of lead time. So what we do instead is we provide a probabilistic forecast that gives an indication of a time frame and amount of an event that would happen. Now, the atmosphere is very much subject to uncertainty, and Ed Lorenz really popularized this thought back in the 1960s when he basically chose to put it in the framework of this three-dimensional butterfly attractor. And the reason the atmosphere is subject to uncertainty is because it's nonlinear, we have advective terms, and we show that it has sensitivity to initial conditions. This is loosely called chaos theory, which implies there's limits to predictability. We're never going to be able to predict atmospheric flow perfectly days, weeks, or months in advance. Therefore, we think in terms of attractors and manifolds in theory, but in reality, what it means is it requires probabilistic forecasts to give us a range of the uncertainty that is in the prediction. Okay, so the idea of this probabilistic forecast is to start with an ensemble of potential, initial, and boundary conditions. You see here on the plot, there's a probability density function at time 0 on the left of the plot, and over the course of time, this PDF is going to evolve. It may not get mapped into a PDF of the same shape or size. It often ends up being something bimodal, such as you see in this example. And the idea is if we integrate our models forward in time, we start seeing the possibilities of what the forecast could be at that later time. So it's due to the imperfect initial and boundary conditions as well as errors and discrepancies in our model formulations. Now, when you do this probabilistic prediction, first of all, the mean is typically a better estimate on average than any single model realization is going to give you. But secondly, it provides a probability of the event at that future time. And knowing those probabilities can be a huge benefit to users. Now, in the paper, we included this chart as figure 1. And it talks about the different methods of making probabilistic forecasts. Number 1 is statistical methods, typically based on a single numerical weather prediction deterministic model. And then any of a range of statistical methods, it could be statistical learning, it could be analog ensemble, it could be kernel density, uses that to quantify the probability. A little bit more complicated are statistically based scenarios. Again, based on a single NWP deterministic model, applying some sort of machine learning or whatever other method, talking about the statistical dependence and producing scenarios that possibly could happen. Then, number 3, we have physically based ensemble forecasts, typically done with multiple NWP models or model parameterizations. We call these physics ensembles. We often post-process them, convert to power, what other variables we need, and that provides a PDF, a better estimate of the mean as well as quantification of the uncertainty. And finally, we talk about the statistical or perturbation-based ensemble forecasts, where often the same NWP model is provided different stochastic parameterizations that can result in different solutions at a later time. This gives a single PDF later that can be interpreted, used to quantify uncertainty. Now, how do these methods compare? If we look at the ensemble versus the statistical method in this figure, we see that the ensemble method is shown by the dark orange outline in this figure. What happened is the black line, that's the measurement that happened after the fact, and the red line gives a statistical estimate of what would have happened in that case, with the blue dashed line providing the 15%, 85% quantiles. We see here that the measurement was well within the orange lines. It deviated outside of the blue lines a bit, but primarily within. And again, we expect it to deviate outside the blue lines about 30% of the time. It shows you that we typically, on the statistical methods, we choose our error bars, we provide them, and it gives us an example of what could happen as part of that range of ensemble spread. Now, what does a full physics ensemble look like? This is an example of 21 physical members of an ensemble, and then on the bottom right, you see the mean of that ensemble. Now, if you look at this really quickly, you'll see that in this case, they all look kind of alike. But if you start looking at details, for instance, of that front in the upper right of each of the figures, you'll see differences in positions, magnitudes of this 30-hour forecast of that front. You can imagine that being the front that came through a region that caused a quick uptake in wind over a period and then a downtake. So it shows that 30 hours out, we are going to have differences, but by using an ensemble approach, we can see what range that might be and estimate the mean. So how do we know whether or not our ensemble is a good match to the uncertainty? We often use validation metrics. One of these is the Breyer score. Basically, when you look at the equation on the left, all it is a mean square difference between what was seen, what was observed, except that in this case, it's in terms of the forecast uncertainty. Now, we often break down the Breyer score in terms of reliability as being the measure of the frequency of the matches versus the actual, and compare that to whether or not we're able to distinguish different events. And then the final term is an uncertainty that is based solely on the observations. Now, you'll see meteorologists often also plotting rank histograms. Typical ensembles are often underdispersive, as in the bottom right red set of histograms, but what we want is for it to be even so that we have the forecast in the bins the right number of times. Then on the top right, we see spread skill score plots, where if an ensemble is well calibrated, its spread will be roughly the same as we would get by doing a skill plot. And finally, wanted to point out there are more advanced metrics like continuous ranked probability scores that is a summation, and it is able to estimate reliability and at the same time as many of the other measures. Now, not all ensembles, as we see from our rank histograms, are perfectly reliable as they come out of the model. So we can improve that by doing calibration. In the example shown here, we see that the initial ensemble has a bias. It may also be spread too widely compared to what is capable in the model. So first, we might do a bias correction so that it becomes more centered. We get the right mean answer. We might want to be able to calibrate it so that it's more sharp, so it has a more narrow range. We want it reliable so that the quantile predicted matches the quantile observed over time. So how do we calibrate it? Here, there's a lot of calibration techniques. I'm just going to give an example of one here where we bin the variance observed versus the mean variance, and we can plot a line through that. And by looking at the intercept, that's the bias, we can simply subtract that, and the slope becomes a correction factor for the variance. So this is called linear variance calibration, but there's a host of other methods too, including ensemble Kalman filter, quantile regression, Bayesian model averaging, a whole host of others that are listed here as well. Now, we're going to talk about the uses of probabilistic forecasts. We spent a little bit of time on why we do ensemble forecasts, but also we want to focus on uses, and that's where we've gotten now. The paper talks about various uses used as input for security calculations, used to fine-tune unit commitment. Tim will talk about that next. Capturing extreme conditions. Pengwei will talk about that. But then the paper also includes examples of forecasting for extreme events such as high-speed shutdown risk, as is done in the Irish case study, and also Red Electrica included an example of their use at the TSO level. I've sprinkled in a few other plots from the paper on this slide and this next one, just to whet your appetite to go look at these other use cases as well. So in summary, the atmosphere is inherently chaotic. Therefore, we choose to do this ensemble probabilistic prediction that both produces better mean forecast as well as an estimate of the uncertainty. The ensemble should be calibrated to be most useful. Research is beginning to show us better ways of creating ensembles, better ways of blending ensemble information versus post-processing, and we're noticing that such probabilistic forecasts are now helping with decision-making. At this point, I would like to pass this on to Tim Miller from Southwest Power Pool, who's going to talk about maintaining awareness of uncertainty.
Thank you, Sue. So at Southwest Power Pool, we really have one focus that we're working on as a balancing authority in the Central Plains of the United States. So our market footprint, our BA footprint, has about 50 gigawatts of load, and we need to match that demand in real time, in day ahead, and multi-day ahead kind of horizons. So we're relying on forecasts like what Sue spoke to.
You don't have control. You don't have control.
Do I not have control yet? Let me see. There we go. Nope, that's... Hey, Sue, would you mind passing WebEx control to me? No. Nope, no, I seem to have it. Maybe not. Let me move that down to my screen so I can see better. Here we go. So the focus for us is three different kinds of load generation and capacity plan forecasts that make it into our systems. Load forecasts, like what Sue was just mentioning, is one big one. The other one is variable generation. For us, that's primarily wind generation. And then the third is the resource capability plans that we receive from the participants in our market. So that can be their planned outages or derates, and those can be planned or unplanned. So all three of these have error in them. Sue spoke to the load forecast error and the uncertainty. The same goes for your input for your variable generation, be it wind speed, temperature, solar exposure. And then the resource capacity is also subject to variations due to equipment failure, scheduling constraints by generator owners, et cetera. So that's the kind of uncertainty we're dealing with as we try to balance the load and plan for the load in the SPP footprint. The next couple slides we're going just to use as illustrations of the way we keep an eye on the uncertainty in those forecasts. So this slide here shows the load forecast error bands that we're used to seeing. It's about 3 years of data, and we see anywhere from not much error, so down there at the 0 megawatts, all the way up to several thousand megawatts of error in our load forecasts. And each layer of error has a more routine or less routine, higher probability, lower probability rate of occurrence based upon temperatures. So that's what this chart is showing you is we can expect to see at certain temperatures a certain amount of error in our forecast. We just know there's going to be error As the forecasting tools become more advanced, a lot of the advances that Sue's mentioning, as those become something that is used and as they continue to be improved, these bands get smaller, but there's still error. So we look at each one of those three inputs I mentioned, and we look at the bands of potential error probability, and then we begin to apply that to our decision making when we make our decisions on what we call committing capacity, which is basically scheduling or lining up generation that needs to be available in the coming days. So this is what load forecast error looks like. The next slide gives you an idea of what it looks like on the wind and solar forecasting. So a different shape, same approach though. We can expect different levels of error at different capacity factors of wind output. And there's different ways you can pivot this data, but this was a pretty good one to show you. The low probabilities of error help us to set the bottom of our band, and then or really the top for us, and then the higher probability of error allows us to set the bottom, because we are looking to make sure that we have enough generation capacity available for the load that we need to serve. So these two inputs, and then not in the slides, but the exact same kind of thing for our resource capacity, we bring all these three together and create reports that our engineers coordinate with our operations staff to attempt to, ahead of time, make those unit commitments. One of the reports, just to walk you through an example, looks like this. We do it for certain time horizons. For each of those time horizons, we assess those error bands that I showed. Then, based on those potential errors, we'll basically stack them and flag any hours of those time horizons where the probability of the error with the other errors all adding up is going to put us in a place where we feel that we will not have enough capacity available to the balancing area. So the equation for this, we call it uncertainty capacity, is the amount of capacity that we know is available, how much is able to ramp quickly, or how much we want to keep there rampable. And then we take out the error that we might see from wind, load, or that capacity planning. And by way of illustration, here's what a report might look like. Basically, we do the math for those time horizons, run these reports daily for future time points, and then create alerts that tell us, there in the red with the purple arrow, that your capacity margin that we've calculated in that equation I mentioned is showing within some error threshold we've set. So we just keep an eye on it. It's a judgment call on how much we want to give ourselves for safety margin. But that reporting and those alerts trigger here at SPP processes where our engineers and operators look at the data more carefully. So if we think we're going to be tight, we'll begin to look at the wind forecast specifically for the hours in question. We'll begin to look at the load forecast specifically for the hours in question. We'll talk to our generator operators and make sure that their capacity plans are solid. One of the other reports looks like this, and here you can see that we've essentially done this math for all the hours of this given day and spread it across all the different probabilities. So in this particular situation, we didn't have any that were meeting our alerting thresholds, which is good, just means it's a clean day. But really our goal is to be prepared in the event of an unlikely error or a likely error, so that when the error comes, we've either prepared for it enough in advance that we have the capacity available, or we've prepared enough for it in advance that we've decided the risk is low enough we're willing to live with it. And then this slide is a graphical representation of the table that you just saw. So in the gray in the background is the amount of capacity we have, and then the variations on that, or really capacity we need in the gray, and then the variations on that in the rest of the chart need to be basically inside of the gray, because we know that once it's outside, we're running a risk of not having enough capacity. So these are some of the tools we use to keep an eye on what errors in our forecasts could result in a situation our operators don't need to deal with in real time, something that we can prepare them for in advance by calling on generation to be available at these times. And we'll just continue to integrate them with the tools as they continue to improve over time. So I'm going to hand it over to Pengwei next.
Thank you, Tim. So both Sue and Tim gave a very good discussion on how to use this probability forecast. In the subsequent slides, I will talk about our use cases at ERCOT. So quickly, what the ERCOT is doing, ERCOT is a independent system operator for the Texas grid. So we are assigned with full primary responsibility to maintain system reliability, run competitive wholesale and retail market, also make sure open sales to transmission. Here is a quick current record for our wind generation. So our highest instantaneous wind generation is 90,672 megawatt, and our highest penetration is 56.16%. So you can see from this wind generation record, and it's very critical to maintain the reliability, because the wind generation has contributed a greater role to the system operation fleet. So unlike this west interconnection or east connection, so ERCOT grid is electrical islanded. We don't have AC synchronized connection with our labeling system. We only have these 5 DC ties connected to the either eastern or western connection system. So this makes the balancing very difficult at ERCOT, because we have to rely on the resources we have at our footprint to balance between this generation and the load. And at the same time, in the past 2 or 3 decades, we have seen a significant shift in our resource capacity mix. So in the past, the coal or gas steam used to account for a large portion of our generating fleet. But today, gas combined cycle units, wind, and coal are top 3 contributing to our total generation installed capacity. So as I speak today, we have probably over 2,000 megawatt installed capacity for the utility scale solar generation. And by the end of 2021, our total installed capacity solar generation could be over 4,000 megawatt. And also, our wind generation capacity has grown very fast in the past. So today we have almost over 20 gigawatt installed capacity for the wind generation, and by the end of 2021, the total installed capacity of the wind generation could be higher than 30 gigawatt. So you can see it's as this wind and this solar installed capacity grows very quickly, both of these generation resources are intermittent and variable. So it's a big challenge for us to maintain this greater reliability. So how can we do it? So the first tool we are use is to have this wind forecast and the solar forecast. So I already talked about basically this weather condition is fundamentally chaotic, so it's very hard to forecast this wind generation or solar generation with 100% accuracy. So also another difficulty in using this wind forecasting is right now the 50% higher or the most likely scenario created for this forecasting is fed directly into our market process. So the market process rely on this 50% higher wind forecast and solar forecast to schedule or commit resources for the next few hours or for the coming days. However, because we have these uncertainties for this wind forecast and solar forecast, how can we incorporate these uncertainties into our decision-making process? So this is a puzzle we try to solve. So we have this developed this wind forecast process over almost 10 years, and since last year we add this second wind forecast service vendor. And if we look at our 50% higher wind forecast, and it is quite a good performance from its performance indicator, MAPE. So you can see for the day-ahead wind forecast performance is for this year is below this 60%, and for the hour-ahead wind forecast performance is below 4%. However, this is the average performance we expect to see on the daily basis, because these forecast errors could be highly skewed to either high end, over forecast end, or under forecast end. So occasionally we have seen the big forecast errors as high as the 3,000 megawatts. So the question is, for this extremely large wind forecast error, what can we do? How can we be prepared for these large wind forecast errors? So here is a similar performance matrix for this day-ahead solar resources and for the hour-ahead solar resources. So I want to emphasize one point. Uncertainty is not something new. And in the past, utilities, grid operators already developed procedures to deal with these uncertainties. Those uncertainties could come from load forecast uncertainties or some forced outages. So the challenge is, as we see a high share of this wind generation and this solar generation in our generation fleet, so this variability is becoming much bigger. So it's very hard to use this past method to continue the current path. And so this is the reason why we look at this probability forecast and to see what is the value it can bring to the operations. So in the past, we really primarily use this answer service to compensate for these variations for this from these uncertainties. So among these answer service products, regulation and this non-swing reserve are more relevant to what we are doing to compensate for these wind and solar forecast errors. So this regulation service are provided by these generations on this secondary primary frequency control to compensate the load change from the minute to minute within this one scheduled time interval. Also, this the non-spin reserve service is provided by this off generation or this load resources or this unloaded generation capacity, which can deliver the full obligations within 30 minutes upon receipt of this deployment instruction. So, however, the current practice at ERCOT is to determine how much answer service quantity we need for the next year, 1 year before. For example, in year 2019, we determined the as minimum requirement for year 2020. So this is this connection between what we really need and the analysis we run for this future year when determining this uncertainty requirement. So how can we blend these different factors and to consider this system reliability and also provide this very good situation awareness to operators. And since 2006, ERCOT developed called Reliability Risk Desk in control room to specifically look at these information, to look at this forecast, both this 50 percentile wind forecast, which is deterministic, and also this uncertainty forecast around these forecast areas to determine whether we are short for generation capacity in the future hours or we have sufficient amount of generation online. So here is a quick view for the tool we developed for the Reliability Risk Desk. It's called the Capacity Available tool. So basically from the left side to the right, so you can see it lists the regulation up and non-spin reserve, also active load forecasting model we are using in the real-time operation. And besides this, you can see when you move to the right side, you can see the forecast for the next 6 hours. So the most critical information is highlighted in this green box. It gives you the wind uncertainty. So it's addition to this deterministic 50 percentile wind forecast you are seeing here. It gives operator some additional scenario for how low the load forecast could be if this is uncertainty. So basically it tells operators more information operator cannot capture from deterministic wind forecast. First one is if this spread is very large, for example, right now it indicates almost 3,000 megawatt uncertainty. This means the weather condition could be very volatile for the next few hours, and it requires more watch out from the operators and to track this operation condition more closely. Second one is it gives operators the quantitatively magnitude of the variations for the wind generation. So by using this and combined with load forecast and the ramp capability and also answer service we have at this moment, operator can specifically look at this surplus or shortage in the wind generation, in the total generation fleet. So here, what I think is one particular example. This blue line represents this total generation capacity without considering any uncertainty from the wind generation. However, if we include the effect of the uncertainty, so this total capacity will drop from blue line to this red line. So the difference between the blue line and the red line is due to this uncertainty in the wind forecast. And at top of this red line, you also have this generation rig up capacity and the non-spin reserve capacity. This is answer series which could be deployable. And so the separation between the generation capacity and the load, which is a gray area, is the online room. So it really provides a very good visualization to the operator to see whether this online room is positive and whether it's negative. Also, it allows operator to explore the different percentile, which is highlighted in the upper right box. So operators can choose between 98th percentile, which is the most conservative result, and 90th percentile, which is a mildly conservative result. And also, we have ongoing work to look at the variations within an hour. So here, what I'm seeing is a prototype. We look at how this variation in the wind forecast within 1 hour could affect the generation capacity. So because this inter-hour variations in the wind could exhaust all these regulation resources, and also it could drag down the frequency control performance. So it is a tool for operator to look at how much the wind generation could change for the next hour. And looking forward, the things I have been talking about is the primary focus on wind forecast. What about the solar forecast? Right now, we are working with the Enriel Utility Dallas and also our solar forecast vendor on a Department of Energy funded project to bring the probability solar forecast into the ERCOT operation environment. So it will be built on our past experience with the wind and the platform, and see how the different probabilities solar forecast with different percentile can affect this generation capacity for the looking ahead the horizons. And I think one personal note from me is I have participated in the ESIC group meeting in the past personally, and ERCOT as a whole benefit a lot from the discussion over there. And definitely this probability forecast is increasing important topic. So we look forward to hearing from others their practice on this. Thank you very much.
Okay, thank you, Pengwei and Tim and Sue. I think I covered a lot of material there. And let's go ahead and move into the questions. And let me remind you that the Q&A box in the lower right-hand corner is open, and that's the way we'll handle the Q&A. Let me begin with kind of a general question as far as the sort of broad or wide-scale applicability of stochastic forecasts and how they've been adopted by the industry. I know we've discussed this in our ESIG meetings that sometimes it seems like they're a little slow on the uptake. They are more complex, but they do have more information. I'm just curious if each of the presenters could give us a little perspective from their own organizations about the rate of adoption of stochastic forecasts in your control room, and how that's been going, how the operators feel about it, and sort of how open they've been, how receptive they've been to the information that's available. Or Sue, maybe from your point of view also for the industry as you see it from your perspective.
Okay, so I'll start off. Meteorologists have been recognizing and embracing the uncertainty of our forecast for some time now. And ensemble forecasting or probabilistic forecasting has become a big thing over the last several decades. But sometimes as meteorologists, we feel like, we can push that information, but until the end user really wants that information and pulls for it, that's when it really becomes useful. So, we're finding that just meteorologists telling about the probabilistic forecast, the possibility of it, was not sufficient. So it's really good from my perspective to see people in industry now asking for that information, in which case that gives us an opportunity as the meteorology forecasting community to respond to that and give the information in a way that is really being requested by the end user.
Okay, thanks for that. And Tim, you want to take a crack at that?
Sure. So for our part here at SPP, our operators who are using these forecasts, their real focus is what they're using accurate enough? Is it reliable enough? Is it consistent enough? Can they trust it? And so they like these kinds of things. The more information we have on the probability of where a forecast is going to land, that gives them more information and more certainty around where the forecast is going. So that's good. As far as integration within, processes and systems, things are, I think, across the board, when compared to, say, the tech industry, much slower to be adopted by utilities in our space. So, when we have a vendor or a software solution come along that fit well into our existing systems, those happen and are implemented more quickly than some of the more cutting-edge things that are still being refined and tooled up so that they can fit into the processes that are going on here. So really, I don't think the comfort level is really a barrier as much as the just complexity of getting the data, sorting it out, making sure it fits into the systems, and then testing it out, ensuring that the support staff are confident in the way it's been implemented, and then rolling it out to the operators. So it's a good development. It's just one that has to evolve in our space at the right pace.
Okay. Pengwei?
Sure. I think general observation is operators really embrace this uncertainty tool when they see the value. So really, it's because it's a nicer tool to tell them the uncertainties around the wind forecast, and especially when they evaluate the reliability. So it is a cutting-edge tool. It requires more education on the operators and also the staff support. But I think the general trend is it is becoming more critical because this is really a tool. The value of the tool really is critical when we have a high share of the renewable.
Okay. There's a question here. I guess it's for Pengwei, but maybe for Tim also. As you get higher and higher penetrations of renewables on your system, that would mean both the wind and the solar. Do you feel like the forecasting technology is adequate? Do you think there's developments that needs to be made? How do you see things evolving as your renewable penetration increases?
So the renewable forecasting technology is evolving, so it is still improving, and we see both the deterministic forecast and probabilistic forecast have a role in the operation. So because right now our market operation still use this the 50 percentile most likely forecast to determine the schedule. However, this probability information is additional add-on and to tell us how this incoming weather could be more volatile, and when this large extreme weather could happen, because it's very hard to imagine the 50 percentile, a single value forecast can give you very good coverage for this large forecast errors. So these large forecast errors could be 3 or 4 times higher than average error you are seeing on a daily basis. So only probability forecast can capture this type of these forecast errors. So this is the reason why we believe probability forecast is very critical, especially this time you need a forecast most. Yeah.
Okay. And Tim, how about?
So we see the variable generation forecasts continuing to improve. We keep working with different partners to make improvements around, I guess what you could call edge cases, some of the hard situations to forecast, keeping pace with new technology in, say, wind turbines and in the solar plants. So we're continuing to look for improvements. Generally speaking, the forecasting has been improving over time, and we have been, satisfied with where it's going. SPP is experiencing anywhere up to 68% of renewable penetration against our load. So it's critical for us to be accurate in the normal day-to-day, which it's generally pretty good, but also in those edge cases that have cropped up all the time. So our approach on those is that it's a learning experience for the industry. Part of that's participating in ESIG. Part of it is meeting with our partners on a regular basis to ask them questions, get more data for them if they could use it, ask for more improvements, and really increase our knowledge and work across the industry and across the space. That's really where our focus has been, because it's got to keep getting better, because it's just going to continue to be an increased challenge for us.
Okay, thank you, Tim. Here's a question that's probably more directed towards Sue, but if Tim and Pengwei, if you have any thoughts on it, I'd be glad to hear those as well. And the question is, what kinds of data do you currently not have that would help improve your model accuracy and resolution?
That is a good question. So oftentimes we do not, to get better forecasts, especially for wind energy, but also for solar energy, it would be nice to have a little more information about the atmosphere than we often do. For instance, if we could have information that would help us derive atmospheric stability conditions, which requires having multiple levels for temperature and wind speed, that would really be helpful. That determines the regime that we're forecasting for. Now, as far as, I'm focusing on general accuracy. As far as the reliability, if we had even more information inside the wind and solar plants on exactly what's happening, and to be able to bring that to bear on the forecasts themselves, it would help us both in making better forecasts as well as better assessing our forecasts. Now, I'm not sure, am I getting to the answer in the way you were hoping there, Charlie?
Yeah, I think so. Data about the atmosphere generally is tough data to get, and would help you do a better job. I don't know, Pengwei and Tim, if you have any thoughts on that or not. If not, we could just move on to another question, and that is the reliability risk desk that you mentioned, Pengwei. I think the first time I heard about a special sort of renewables focused desk was with Africa of Spain, and then I think that was probably goes back 10 years or so, and then Cal ISO, I think, had a renewables desk. Now you've got a reliability risk desk, and what would I like to hear from Tim also, if they have any thoughts in that regard. But Pengwei, what motivated the reliability risk desk at ERCOT, and how do you use?
So basically the source why we need this reliability risk is operators did a very good job in the past in committed resources and maintain the reliability and for the typical load pattern. And as we increase the share of the renewables, the operating condition will become more varying. So it will be not a repeat. For example, today's operating condition will significantly different from what we saw yesterday. So really to maintain the reliability, we need some tool to look ahead to evaluate this variability on this system reliability on a holistic environment. So before we add this reliability desk, operator tends to look at things in isolation. For example, how good the wind forecast performance has been in the past few hours, and how much ancestors we have by, and but this reliability risk test really is providing look-ahead study to evaluate these various operation conditions and to assess the impact on the reliability. It look at the forecast uncertainties, inertia, answer service, and also potentially voltage control. So it really is dedicated to evaluate this risk for the look-ahead horizon.
Okay, thank you, Pengwei. And any quick thoughts on that, Tim, or is that for a future topic?
Yeah, so SPP hasn't set up a desk like this. What we've done is we've set up a team of day engineers who have an on-call rotation, and they hit basically the time periods where we've identified that it's riskier, and so they jump in and look at that data. So that's been our approach to it. That may evolve more in the future. It's already evolved from what was a shared on-call rotation of engineers across teams to a official group of engineers who are doing it. That's been our approach.
Thank you, Tim. I think we're running out of time, so I'm going to go ahead and wrap it up. As I mentioned earlier, an email will go out once the presentations and the audio file are posted. We'll also be posting responses to the unanswered questions once they're ready. We appreciate your engagement. We look forward to seeing you at our next webinar on November 21, which will feature a discussion of the integrated planning environment led by Aidan Toohey of EPRI, the topic of increasing interest given the increasingly blurry distinction between T and D with the rapid expansion of DER, so I hope you'll be able to join us. And just a reminder that further information on all the webinars and meetings can be found on our website at www.esig.energy under events and in the newsletters and informational emails. So Sue, Tim, Pengwei, I want to thank you again for this very timely and informative webinar, and thank all of you for your interest. We look forward to seeing you next week at the Fall Technical Workshop in Charlotte or next month with Aidan on the planning webinar. In the meantime, take care, everyone, and thanks again for your participation.